Hey there guys, welcome to Unit 8, Note C. I've got Note C broken down into 3 little subsections. In the first part, we're going to talk about colligative properties with molecular compounds, and then for part 2, we'll talk about the same type of properties but with ionic compounds. And then in the third section, we're just going to work some problems together. So the first part, what is a colligative property? Well, colligative properties depend on the number of particles, not the type of particle or the size of the particle, but actually how many different little pieces would break down in a solution. So say you have a sodium chloride solution. It would break down into 1 sodium and 1 chloride ion, 2 ions, so it would have twice the effect on these properties. Whereas a sugar compound, sugar is covalent, and so it's not going to dissociate in water. And so then it would just have 1 as its particle number, and so it wouldn't have a multiplier on the properties that we're going to see. Something that has a lot of ions. Let's take aluminum sulfate. It would have 2 aluminums and 3 sulfates, and so that would break down into 5 particles. It's going to have 5 times the effect on our colligative properties. So now you kind of get the idea of what I mean by number of particles. Let's look at some of the properties that we're going to be affecting. So first of all, we could affect the vapor pressure, the pressure of the gas on its own liquid at equilibrium in that closed system. We could also affect the boiling point, or in the same turn, the freezing point. And yes, you will always raise the boiling point or lower the freezing point, basically expanding the temperatures at which we remain liquid. And then another one you may have heard of in biology is osmotic pressure. We're only going to focus on 2 for our notes today, the boiling point and the freezing point. So let's first look at boiling point. Typically, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. So if we're boiling at 100 degrees Celsius, what is it that could cause that liquid to stay a liquid even past 100 degrees Celsius? Well, if you put a solute in that does not want to become a gas, it's basically like a bad influence on those other liquid particles. It's going to convince the liquid particles of water to stay liquid for longer. And the more particles there are, you can think of that as being a stronger influence. More particles saying, no, don't boil, no, don't boil. The water is going to stay liquid for even longer and at even higher temperatures. So if I have a substance that is what they call volatile, it would like to become a gas, and water is fairly volatile. It typically boils at 100 degrees Celsius. And then if we put in a substance that's not volatile, so if our solute does not easily become a gas, then that's going to kind of affect the boiling point of the water, always elevating it to a higher boiling point. So we can actually calculate how much a substance will affect the boiling point of a solution. So this is our formula. Delta T would be the change in temperature. And notice there's a subscript B. We're also going to look at delta TF. So B would be for boiling and F would be for freezing. It's equal to K, which K is a pretty common letter, usually means some kind of constant. So this is the K for boiling. So we have a constant that'll be given. And for water, that number is 0.52 degrees Celsius per molality, lowercase m. And then the lowercase m in the formula is molality. And you can see how that will make our units cancel. So Kb is different for every substance, but remember that water is the most common solvent. So if it doesn't tell you that it's water, or if it doesn't tell you that it's something else, you would assume it's water. But if it does tell you that there's a different substance involved, then they will either be giving you a different Kb, expecting you to look it up possibly for homework, or you would be solving for the Kb, for a different substance. But for water, it's always going to be the 0.52. All right, so let's look at our first problem. What is the normal boiling point of 2.5 mole glucose? What does normal even mean? Well, it's not normal versus abnormal. It's not weird. What does normal actually mean in a chemistry context? That would imply a normal pressure of 1 atm, which means our normal boiling point of 100 degrees Celsius would apply. So that's actually kind of important when we go and translate what is our change in temperature and what does it mean. So one piece of information that they actually gave us here was that the molality is equal to 2.50. One thing that I have to know is when I'm talking boiling point of a solution where we would assume the solvent is water, I also have my Kb, which was 0.52 degrees Celsius per molality. So this is going to allow me to use that first formula, delta TB equals KB times the molality. So when we solve for delta T, I'm basically going to be multiplying my 0.52 times my 2.5. Notice the units, molality on the bottom, molality on the top, and my answer for delta TB is going to have the units of degrees Celsius. So what is 0.52 times 2.5? I get 1.3. This is multiplication, and so we've got 2 significant figures versus 3. So I'm going to go with 2 significant figures for my delta T. So does this mean that this solution, where water is the solvent, would boil at 1.3 degrees Celsius? Does that make sense? No. No water-based solution is going to boil at 1 degree Celsius. That's ridiculous. What it means is that's the change from the boiling point. So we know that the regular boiling point is 100 degrees Celsius. And so then we're going to add 100 degrees Celsius because we know that it would boil at a higher temperature because the boiling point's always elevated. Now, when we add, we go by decimal places. And it may look as if we're going to lose a lot of decimal places, but also keep in mind that 100 degrees Celsius is an exact number, which won't limit our sig figs. So basically that means that your decimal places for your delta T and your T should match. So the actual temperature from boiling, notice I dropped the delta, the actual temperature is 101.3 degrees Celsius. Because I've added this solution, I'm going to have a higher temperature. Or I should say because I've added the solute and made a solution, I'm going to have a higher temperature for boiling. Most common mistake here is leaving the delta T as the temperature for boiling. Just think of it logically. We know that water wouldn't boil at a temperature that high. Or I'm sorry, that low. We want to go to a higher than 100 degrees Celsius. All right, let's look at another question. So this time, it gives me the mass of my water and it gives me a temperature. It does say that it is water, so that also means that I know the KB because we have water as our solvent. So let's start off with a list of variables. Starting with that KB, so I don't forget it, 0.52 degrees Celsius per molality. The next thing that I have was the 535.5 grams of H2O. So what could I use the grams of? Well, we know grams is mass. It's also really important, considering all of our different types of calculations, that we know whether we're dealing with the solute or the solvent. So the H2O would be our solvent. The other thing that we have is the temperature for boiling. So that was 101.5 degrees Celsius. So what I'm seeing here is something with temperature and something with KB, which leads me to believe that I could use the formula delta T equals KB times molality. But is 101.5 the delta T? No, it's just the actual temperature. To get the change from 100, we're going to have to subtract out 100. And so my delta TB would be 1.5 degrees Celsius. Remember, keep your decimal. So then if I plug in 1.5 degrees Celsius for the temperature and the 0.52 degrees Celsius per molality, I can then solve for the variable molality. So notice this is a unit and that is a variable. It gets a little confusing. So if I want to isolate my variable of molality, that would involve dividing by 0.52 degrees Celsius per molality. And you can see the degrees Celsius would cancel, and then molality on the bottom of the bottom is really on the top. And molality is my units for molality, of course. So now I just want to know what is 1.5 divided by 0.52. 1.5 divided by 0.52. And we get 2.88, which will round to 2.9 for the two significant figures. Now that I have my molality, I can start making progress towards my amount of solute. But I'm going to need another equation for that. So I'm going to erase my variables up here and work in my next equation. What version of concentration relates your amount of solute and your amount of solvent? That's going to be our molality equation, which is fortunate since we just found molality. So molality is equal to mole of solute over kilogram of solvent. So now I can plug in the molality that I found over here on the left-hand side, 2.9 molality. So now what do I have that I know from the givens? Do I have information about the solute or do I have information about the solvent? We have information about the solvent. We have the 5.35 grams of water. The problem is, by definition, molality has to be per kilogram. So we can convert that 535.5 grams over 1 gram on the bottom, mole on top, not mole, sorry, bad habit, kilogram on top. We know 1 kilogram is equal to 1,000 grams. So essentially I'm moving my decimal back 3 places. Kilogram, that was the whole point. So if I plug that into the bottom, this 0.5355 kilogram, when I solve for the number on the top, it will automatically be in moles of solute due to the definition of molality. So let's do our 2.9 times the 0.53 times 0.5355. And so we get 1.5, it's 1.54. So 1.5 with 2 sig figs moles. Did we answer the question? Done a lot of work to get to this point, but it does specifically ask for grams. So how do we go from mole to gram? Well, that's our good old mole conversion. So mole to the bottom and gram on top. 1 mole equal to the molar mass of sugar. Regular sugar molar mass is about 180, I don't remember the decimals, grams per mole. So now I'm going to take the 1.5 and multiply by the 180 in order to get the final molar mass of our substance. Or not molar mass, actual mass of our substance. That's going to give me the amount of solute I've put in. So let's use the PowerPoint to recap. First, I used the delta T formula, where delta T is equal to Kb times the molality. Then I was able to plug in the delta T by finding the difference from 100 and using the Kb in order to solve for the molality. That molality could then be plugged into the molality formula in order to solve for the moles of the solute. Then we were able to multiply by the molar mass in order to get the actual grams of the solute in the end, making our final answer 290 grams. All right, so that's all about boiling. Now let's move on to freezing. Where our boiling point always went up, our freezing always goes down. We're going to lower the freezing point of the substance. And so when we find delta T, we want to then compare that to below 0. The formula looks very similar to our delta TB formula. In this case, I've got delta TF equals KF times the molality. So KF is a different number. It is 1.86 degrees Celsius per molality. That's again just for water. If you had a different substance, they would either have to give it to you or have you look it up from an appendix, or you would be solving for it for a different substance. But for water, you should know it's 1.86 degrees Celsius per molality. And again, delta T would tell you the change from 0. So typically that's going to be a positive number, and then you would go that far below 0, essentially giving you the negative answer. So let's look at our first example. Again, I have a 2.5 mole solution. So my molality is 2.50. I know it's freezing And it didn't specify the solvent, so I'd assume that it's water, making my KF 1.86 degrees Celsius per molality. So my formula, delta TF equals KF times the molality. I'm going to plug in the KF of 1.86 and the molality of 2.50. So what is my delta TF then? How far below freezing is that? 1.86 times the 2.50. So that is 4.65. So does that mean that this solution would then freeze at about 5 degrees Celsius? Well, no. We know that water won't freeze till at least 0 degrees Celsius, and then a solute would make it freeze at an even lower temperature. It's the normal freezing point of water, 0. And so if we find that much lower than 0, it would be negative 4.65 degrees Celsius. So essentially it's the negative answer because you're going below 0. All right, let's look at one finally where the solvent is not water. This time we have a solvent of formic acid, actually. So let's look at what it's giving us. We have 15 grams of a substance dissolved in 750 grams of the formic acid. So the 15 grams, the thing that's being dissolved in something else, would be my solute. And so that 15.0 grams would be the mass of my solute. Whereas the mass of my solvent is 750 grams because it's dissolved in the formic acid, making formic acid the solvent. Notice that it's not water, so I'm not adding the KF to my list of variables. Since I have an amount of solute and an amount of solvent, let's go ahead and find our molality, and then we'll revisit this to see what we need to do about these temperatures. So first, molality is mole solute over kilogram solvent, which means I need to convert both of these numbers because the solutes in grams, not moles, and the solvents in grams, not kilograms. So this solute in grams, 15.0 grams, we need to convert to moles. So that's going to be your mole conversion. Or 1 mole over the molar mass of the C2H5OH. That will give us our moles of solute. Then we're going to convert our mass of solvent from grams to kilograms. So as you remember from the last example, that essentially means we're moving our decimal back 3 places. So it's going to be 0.75. And there was no decimal here, so this is actually just 2 sig figs. So 0.75 kilograms. So I can plug that directly in here, but I do need to find my molar mass of the C2H5OH to divide and get my moles. Then I'll be able to plug that answer into the top. Once I have moles of solute and kilograms of solvent, then you can divide to find the molality. So what does that look like? So my molar mass was about 46 grams per mole, making my solute a 0.3261 or 0.36 moles of the solute, divided by the 0.75 kilograms, would make my molality 0.4348, or with 3 sig figs, 0.435 molality. Now that I have the molality, I can start thinking about my next formula. The next formula was the delta T equals the KF times the molality. But what is going on with my delta T's here? I have 7.20 degrees Celsius and I have 8.40 degrees Celsius. The pure formic acid would give you basically the 0 degrees Celsius for water. What does water freeze when what temperature does water freeze at when it's pure water? 0 degrees Celsius. So where are we starting? The pure stuff, 8.40 degrees Celsius. And then once we drop to 720, we are lowering that freezing point. We now have the solution. So what is the difference between the 8.40 and the 7.20? So our delta T would be the difference between those two, which is 1.20 degrees Celsius. Notice that we're keeping the decimal places, 2 decimal places, 2 decimal places, so my delta T is the 1.20. So now I'm going to plug that into my formula, which was delta T equals KF, delta TF, sorry, equals KF times the molality. And we just determined the delta TF is 1.20 degrees Celsius. The KF is 1.86. No, it's not. The KF is what we're solving for. Sorry, bad habit. Because it is not water. And then the molality that we just solved for up here, 0.435 molality. Because this should have had 2 sig figs. So let's go 0.43 molality. All right, so in order to isolate the KF, we're basically dividing the delta T by the temperature. I'm sorry, by the molality. Can't talk straight today. So if we take our delta T of the 120, the difference of 120, and we divide it by our molality, we get a KF of about 2.8 degrees Celsius per molality. Right now, with our first time through with delta T, by the way, I'm not super worried about the sign of your delta T. But you can see here that actually, because we decreased the 1.20, it would make our KF negative. And yes, some KFs are negative and some aren't. It does matter the sign of the delta T in our next unit, Unit 9 on thermodynamics. The sign is a huge deal. So if you want to try to think through it, it may help you kind of get in good habits for Unit 9. But as of right now, I'm okay if you can at least get the number. So we're looking at the change in temperature compared to the molality of the substance. That's essentially what KF gives us. All right, one last example. Let's do this. So we've got this antifreeze solution, and it has a volume, it looks like, 50 cubic centimeters for this ethylene glycol, 50 cubic centimeters. But then it gave me a density of that same substance in grams per cubic centimeters. So density can actually be used to convert volume to mass. Isn't that what density kind of is a ratio of the mass and volume? So that kind of tells me I'm going to be doing some kind of conversions out of volume into grams and then maybe towards something else. The other thing it gives me is gram of water. So we know water would be our solvent. So that must make this ethylene glycol my solute. I'm putting that in to be dissolved. And then the question is, will it protect it from freezing? So basically we need to figure out how far down we will depress the freezing point. So let's start with what we know about the solute. The solute is 50.0 centimeters cubed. Eventually I want to use my molality equation, which was moles of solute per kilogram of solvent. So the solute needs to get turned into moles. But right now it's in volume. So the first thing that I'm going to do is steal this density to get towards gram, because then I would be able to go from gram to mole. So first I'm going to put my cubic centimeters on the bottom, gram on top, and then to take it to the moles, gram on the bottom, mole on top. So the gram per cubic centimeter is what they've given you in the question. So instead of like we're water, the density would be 1 gram per cubic centimeter. For this other substance, it's 1.12 gram per cubic centimeter. So per 1 cubic centimeter. And it's always 1 mole. And then here we would need to find our molar mass of the C2H6O2 and plug that in. Once you convert that, you can get into moles in order to be able to plug that into the top here. This answer would go into our molality equation. The other thing we need is kilograms of the solvent, and it gave me grams of the solvent. So if you look at just the solvent, it's this 50.0 gram. So I'm going to move the decimal back 3 places. And it did have 3 sig figs, so we're going to stick with that. 0.0500 kilograms, which is now what I can plug in for kilograms in my molality equation. And then I can divide those two things in order to get the molality. So let's go ahead and take it that far in the calculator. First, we've got the molar mass of about 62 grams per mole, and then that'll give us the moles of 0.90323. The kilograms was the 0.05, and so if you divide those, you get a molality of about 18, or 18, suffix would be 18.1. So now that I have the molality, can I start working towards a temperature change? What else do we know? Since it's water, we know that the Kf is equal to 1.86 degrees Celsius per molality. So if I have the Kf and I have the molality, I should be able to find the delta T. So I'm just going to plug in the Kf and the molality in order to solve for my change in temperature. So when we multiply these together, we get a change of 33.6 degrees Celsius. So does that mean that the solution would boil at 33 degrees? No, this is just a change in temperature. It's going down from 0 since it's water. So if it went down from 0, 33.6 degrees, then this solution would not freeze until it reached negative 33.6 degrees Celsius. So back to the original question, would it protect this car on a temperature, or at a temperature of negative 23.3 degrees Celsius? Yes, it protected at negative 23, at negative 25, at negative 30, all the way down to negative 33. So yes, it will protect the car because it will depress the freezing point beyond the temperature of the car. All right, guys, that's going to wrap up our molality equations being tied into colligative properties. So our new formula using delta T as a function of a constant times the molality. This is going to allow us to figure out how high the boiling point would elevate or how low the freezing point would depress. Remember, you're always going up or down from, up from the boiling or down from the freezing. All right, that's going to wrap up the first section of Note C, Part 1. In Part 2, we're going to look at the same types of formulas. We're still going to have a delta T equation. We're going to look at colligative properties, but using ionic compounds, and we're going to look at how that changes. I'll see you in a minute. Hey guys, we're going to continue with colligative properties, but in Part 2 of Note C, we're going to look at colligative properties as they relate to ionic compounds. There's one thing that'll be very different than the same properties with molecular compounds, and that is the number of particles. And if you remember, colligative properties are all about the number of particles. Molecular compounds do not dissociate in water, and so everything we looked at in Part 1 had one particle. So what happens if you have more particles? Well, first let's go over a little bit of vocabulary. Electrolytes basically mean that we have ions in solution. And so the way that a lot of these questions will be phrased will be telling you that you're dealing with an electrolyte, and that's when you know that you need to be on the lookout for more particles. So we already know that the ionic bond is what's going to dissociate, but the thing we haven't really talked about yet is there's different degrees of dissociation. Some things break down completely, whereas some things only partially dissociate. The more ions that are in solution, the better of an electrical conductor or an electrolyte you will have. The idea here is that if something completely dissociates, then you would have the best conductor. Whereas if you have something that doesn't dissociate at all, like a covalent compound, then that would be a terrible electrolyte. We actually call them non-electrolytes. So I have this kind of organized in a table. The good electrolytes are going to be really good at conducting electricity, hence their name. So these compounds are going to be ionic compounds that go through complete 100% dissociation. So your typical salts like sodium chloride or magnesium oxide should 100% dissociate. And then strong acids and strong bases will completely dissociate. And I'm going to give you a list in just a minute. You can also have partial dissociation, which would basically mean you do have some ions in solution. Let's take hydrofluoric acid, for example. You've got your H and your F. Your hydrogen is going to dissociate from the fluorine, and it will break up into ions. The problem is those ions are also going to recombine and form molecules again. So you have some things that are breaking up into ions, some things that are recombining to form a molecule, and we'll eventually reach something called an equilibrium here. So you would have at any given time some ions and some molecules. Well, that's not going to be as many ions as if it was only a one-way thing, only producing ions. So when you have compounds that partially dissociate, basically meaning that they have some type of reverse reaction, you are going to be less good of a conductor. We call them poor conductors or bad electrolytes. So weaker acids and bases would fall into this category. You could also have a non-electrolyte. So those would be the covalent compounds that we talked about. Anytime you have something that does not break up into ions, you're not going to have anything there to conduct electricity, because the electricity is basically flowing electrons, which are negative. They need to be pushed and pulled, attracted and repelled through charged substances. So if you have a molecule that is not charged, it's not going to be good at conducting electricity. And so here's where you get your non-electrolytes. What we did in part 1 was only working with non-electrolytes. Now I want to look at some things that break up into different particles. So I mentioned that I'm going to give you a list, so I want to do that first so you can tell the difference between strong acids and weak acids. There are exactly 6 strong acids that will 100% dissociate in water. 6 and only 6. It's on the list or it's not. These 6 things, hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, nitric acid, and perchloric acid, will 100% dissociate. Anything else not on this list will not 100% dissociate. So it's these 6 and these 6 alone. Your strong bases will always have hydroxide as the anion, and their cation will come from your alkali metals or your alkaline earth metals. No transition metals, no metalloids, just the group 1 and group 2. If you've got like sodium hydroxide or magnesium hydroxide, that would then be categorized as a strong base. So only those compounds would 100% dissociate. Anything else that doesn't fit into these categories, we would say would be a poor electrolyte, or it would be not as good at conducting electricity. So what does this all have to do with colligative properties? Well, remember, colligative properties depends on the number of particles. So if I have dissociation, if I'm breaking down into ions, I'm going to increase the number of particles in solution. That increase in particles is going to then produce a greater effect on those colligative properties. So, for example, let's say we're looking at a compound where we have sugar, only 1 particle. You should recognize this number as the Kf of water. This is how much we would change the freezing point of that substance that would be containing a molecular compound. If I used salt, NaCl, as my compound instead, which would break up into 2 separate particles, the sodium ion and the chloride ion, I would have essentially doubled the effect. So 1.86 would double to 3.72. I would have twice the effect on the freezing point because I have twice as many particles pushing around the water molecules to lower their freezing point or raise their boiling point. More particles would just continue to be a multiplier. If I had 5 times the particles, I would have 5 times the effect on the freezing point. This is essentially a multiplier, and it looks exactly like that in the formula. So delta Tf equals Kf times m, that was our formula for the molecular compounds, because it only had 1 particle. And what does multiplying by 1 really accomplish? Not a whole lot. So they don't even bother writing the n when they're working with molecular compounds. You could consider n just to be 1 for molecular compounds and just always use this version of the formula. Same effect. But if we're breaking into multiple particles, we are going to have a greater effect here. We're going to increase the effect on our change in temperature, whether that's boiling or freezing. So delta T, M, and Kf all still mean the same thing, and now we have a multiplier of the number of particles. So let's look at an example. We have a 1.15 molality sodium chloride solution. So yes, I have the molality, M equals 1.15. I also know that the solvent would be water because it didn't say otherwise, which means I have the Kf of 1.86 degrees Celsius per molality. But what I need to find now that it's an ionic compound or an electrolyte is N. N being the number of particles. So let's think about sodium chloride. Sodium would be Na with a charge of +1, and chloride would be Cl with a charge of -1. So when you do your crisscross, you get NaCl for a final compound. How many particles would this break up into if you split your sodium and your chloride? I have 1 sodium and I have 1 chlorine. 2 total ions. So N would be 2. So now I can plug this into the delta T formula. Delta Tf equals Kf times M times N. So let's find our change in freezing point. using the 1.86 degrees Celsius per molality, my 1.15, oops, that's a 5, I promise, 1.15 molality, and the N now of 2. See how the number of particles is literally a multiplier for what the delta T would be. So what is the freezing point if I now work out this mathematically? So let's punch that in the calculator, see what we get. All right, so we got our 2 particles, we've plugged in the formula. We should get a delta T of 4.28 degrees Celsius. So does that mean that the solution is freezing at 4 degrees Celsius? No, remember we're going down from 0. So it would actually freeze at negative 4.28 degrees Celsius. If we were using this formula to find delta TB, we would then go up from 100. All right, let's look at a slightly different question. The only thing I'm going to change here is the substance itself, calcium chloride. So I still have the molality of 1.15 and the Kf of 1.86. But now I need to find the N for calcium chloride. So calcium is Ca and chlorine is Cl, but calcium has a +2 charge where chlorine has a -1 charge. So if you crisscross that, you get CaCl2. Meaning I would have 1 calcium, if I broke this up, 1 calcium and 2 chloride ions. So if I have 1 cation and 2 anions, that's now a total of 3 particles in the solution. So then I'm going to write this out. I'll just go ahead and do it this way. Where I've got my formula, delta T equals Kf times M times N. Using the N of 3 this time would get me a higher delta T. Delta T of 6.4. Remember when we had the N of 2? The change was about 4 degrees Celsius. With the N of 3, we have a change of about 6 degrees Celsius. So it is increasing proportionally. So is this the temperature where the solution would freeze? No, we've got to go again down from 0. So the temperature would actually be negative 6.42 degrees Celsius. Let's do one last one. Now I've got a polyatomic ion involved, our calcium phosphate. Again, I have the molality of 1.15 and the Kf of 1.86. But now I need to find the N for calcium phosphate. This one's a little tricky. So calcium has a +2 charge and phosphate, PO4, has a -3 charge. So when you crisscross, you get calcium 3, and then we're going to put phosphate in parentheses with the 2 on the outside. This would be the correct formula for calcium phosphate. So when it splits, the dissociation will break apart calcium ions from phosphate ions. Calcium Ca, there are 3 of them. PO4 is the entire formula for phosphate, and there's 2 of them. The 4 is part of the formula, the 2 is the count. We have 2 phosphates. So that would be a total of 5 particles that calcium phosphate would break up into. 3 cations and 2 anions. So once we know that, we can start plugging into our formula again, using the same formula with the N multiplier. When you plug in your Kf, the molality, and then this time an N of 5, you're going to get 5 times the effect on the delta T, or about 10. So we need to now find the difference from 0, or negative 10.7 degrees Celsius. So when N was 2, there we go. When N was 2, the change was about 4. When N is 3, change is about 6. And when N is 5, the change is about 10. So you can see this proportional change because the number of particles is literally the multiplier on the effect for the colligative properties. All right, that's going to wrap up this new part about what to do with the electrolytes using the number of particles as a multiplier. There's one more short section on notes C. In part 3, we're going to work through 2 separate equations, 2 separate problems. The problems are just a bit long, so I put them off in a separate section. So we'll see you on that note C, C3. Hey there guys, welcome to Unit 8, Note C, Part 3. We're going to work through 2 kind of complicated examples. We're just going to take it a piece at a time, step by step, and we're going to find the solution. So let's start with our first question. The first thing that I usually do with word problems is break them down so they're not word problems. So I'm going to start by making a list of variables here on the side. The first number I come to is that I have a 1.2 gram sample of an unknown molecular compound dissolved into something else. That would make that my solute. So I have the mass, since it's in grams, of the solute. And that's going to be the 1.20 grams. Another important word here is that it's a molecular compound. The word molecular means it's a covalent compound. And we know covalent compounds do not dissociate in water. So I know that it would only have one particle. So N equals 1. It's going to be dissolved in 50 grams of benzene. So whatever's doing the dissolving would be our solvent, right? So benzene would be our solvent. So the mass of the solvent is going to be this 50 grams. Equals 50.0 grams. Now it's giving us some temperatures. We have a solution that freezes at 4.92. We're trying to find a molar mass. And then it says pure benzene will freeze at 5.48. So we have the temperature of the pure substance, or I should say the freezing temperature of the pure substance, which was the second one that they gave us, of 5.48 degrees Celsius. And then the solution freezing point was this 4.92 degrees Celsius. So whenever they give you two temperatures, you can find the delta T, or change in temperature. So let's do this one with correct signs. We've got delta T is always going to be equal to the final temperature minus the initial temperature. So that's pretty much a formula there for you. Whenever you're finding delta in chemistry, it's usually final minus initial. So you've got the final temperature of what the solution ended up as, delta T equals 4.92 degrees Celsius, minus the initial temperature, or whatever it started as with a pure substance, this 5.48 degrees Celsius. So that means my delta T is actually a negative, and find the difference here, we have a negative 0.56 degrees Celsius. So that's all my work with temperature to find the delta T. The one other thing that I want to add to my list here is the KF, which, since the solvent isn't water, it's not the typical KF of 1.86. It's actually a negative 5.12 degrees Celsius per molality. So now I want to start looking at which formula I can use first. There are two main formulas involved in these types of equations, or types of problems. We have delta T equals KF times M times N, and we have that the molality is equal to the moles of solute over the kilograms of solvent. So the question is, what do we have enough to use? So we have the mass of solute, but I can't convert to moles since I don't know the molar mass. So that's not helpful right now. We have the mass of solvent, which could be helpful because I have grams and need kilograms. I do know I will need to convert that to use it. I also have the delta T, which we found by finding the change in the temperatures. And then I have the KF, and then I knew it was molecular, and therefore I have the N. So where I only have one part of my molality equation, I have 3 of the 4 parts for my delta T equation. So I'm going to start by using the one I have enough information. And I'm going to use that to solve for the molality, and then plug that in and be able to now start working towards moles and keep going. So let's start by plugging in the formula delta T. So delta T we decided was negative 0.56 degrees Celsius, and the KF is negative 5.12 degrees Celsius per molality. Now I'm solving for the molality, but this is the variable molality. So I'm going to put that in a different color, maybe a darker color there, so that I know I'm not canceling out a variable with a unit. This is unit molality, this is variable molality. Okay. So then the N, you should know you either don't need the N in a molecular compound, or we could even show plugging in the 1, which you know isn't going to affect the calculation any. So in order to isolate the variable molality, I'm going to need to divide the delta T of negative 0.56 by my K value of negative 5.12 degrees Celsius per molality. So what is my molality when I do this division here? You're going to get a molality of 0.11 molar. Now I can plug that in, like we said, in this equation. Plug in the molality and plug in my mass of solvent, but in kilograms. So first, the molality on the left is the 0.11. I don't know the moles of solute, so I'm going to be solving for that. On the bottom, I'm going to be solving for the kilograms of solvent. So if I'm given grams and I want kilograms, we're moving the decimal back 3 places. So it's going to be 0.0500. Keep your significant zeros. But now I have kilograms. So that's going to allow me to solve for x by multiplying my kilogram times my molality. And so we get x equals 0.0055 moles. I knew that was moles because of where I was solving for in the equation. Because I'm solving for x on the top of the molality equation, by definition, that has to be moles. But in order to get molar mass, I need my grams per moles. So remember, we can use the molar mass formula the molar mass units essentially as a formula. So if molar mass is grams per mole, and I'm trying to find the molar mass of the solute, I have the mass of the solute from the very beginning. That was the 1.20 grams. I just didn't know how many moles. But working through the delta T equation and then the molality equation, I was able to derive the number of moles. So now if I put that in the denominator, 0.0055 moles, and I do this division of 1.2 grams divided by 0.0055 moles, that will get me the molar mass in grams per mole. And so we get 218 grams per mole. But we did have 2 significant figures coming all the way back to the delta T of 0.56. So notice I rounded my molality and my number of moles to 2 significant figures. So I'm going to want to do this as well. So instead of 0.18, we're going to round this to 0.20 grams per mole for our final answer with correct significant figures. 220 grams per mole. So that's our first question. One more to go. Let's swap out our question. Now let's start our second question. I'm going to do the same thing. Since I see a word problem, I'm going to start by listing out my variables. It's going to make it easier to see what formulas I can start with. So the first number that I come to is the 37 grams. So I'm going to write down that this is a mass, and now I need to determine solute or solvent. So this is the compound that was dissolved, so that would be solute. The mass of the solute is 37.0 grams. It's dissolved in 200 grams of water. So water, being our universal solvent, is obviously, this is giving us the mass of the solvent at 200 grams of water. Now, since the solution froze at negative 5.58 degrees Celsius, so this would be the freezing temperature of the solution, negative 5.58 degrees Celsius. And then it just asks for what is our molar mass. The problem is it didn't give us the normal freezing point. But since we know it's water, we should know the normal freezing point. Normal freezing point of water is 0 degrees Celsius. So our pure substance, or pure water, would freeze at 0 degrees Celsius. And so we can find the difference there of 5.58 degrees Celsius, which is what we'll use for our delta TF. The difference between where water would normally freeze and where it froze in this situation. So what do I have in relation to my formulas? Let's go ahead and write out the formulas so we can kind of compare. I know delta TF is equal to KF times M, and then when it's ionic, we have to worry about N. Now, was this ionic? New covalent compound. So that tells me that N equals 1, so I'm not worried about N. I also know that molality is equal to the moles of solute over the kilograms of solvent. So now what do I have compared to these formulas? Well, I know I have my delta T I found down here. I know I have my mass of solvent, and I can convert gram to kilogram, so that's that guy. But I have the mass of the solute, and I want moles of solute. And normally that's no problem, but I don't know what the substance is. So that means I don't have a molar mass, so that's not helpful. So it looks like I only have one thing in my molality equation and one thing in my delta T equation. But wait, it was water, right? And so that means that the KF is 1.86 degrees Celsius per molality, which actually means I have two things in my delta T formula. So let's plug those in. Delta T of 5.58 degrees Celsius is equal to my KF of 1.86 degrees Celsius per molality. And then I'm solving for the molality. And again, I'm going to put that in a different color so that I can make sure not to cancel a variable with a unit. So now to isolate this variable, I'm dividing by the KF, 1.86 degrees Celsius per molality. And so I get a molality of 3 with 3 significant figures. So now that I have the molality, now I have enough variables to start using my second formula. So I'm going to start with molality on the left, the 3.00. I don't know the moles of solute, and like we talked about, I can't get it just with molar mass. So that's my X. What I need now is the kilograms. So again, we're going to move the decimal back 3 places, and the mass of the solute will be 0.2000. Keep your significant zeros. Kilograms. This is going to now allow me to solve for X, which by definition of molality will be the moles of the solute. So what do we get when we do this multiplication? We're going to get 0.6. We're going to keep it to 3 significant figures over the 4. So 0.600 moles. Now we're much closer to finding molar mass. Let's think again, what was molar mass? Always grams per mole. So the gram was what they gave us back in the beginning here, the 37.0 grams. And I'm going to divide that by the moles that we just found from using these two formulas together, 0.600. And then I'm going to get an answer of 61.8. 3 significant figures in each, so I'm going to keep it like that. And the units will be grams divided by moles, or grams per mole, which is perfect for molar mass. So our final answer is 61.8 grams per mole. We did it, guys. We solved both questions. The next set of notes that you're looking for are for Unit 9, where we're going to study thermodynamics. I'll see you there.